Hello students, welcome to my YouTube channel. In this video lecture, we are going to answer the next questions from sample paper number 7, BALI navigation book. So let's start with question number 71. A pitot tube covered by ice which blocks the ram air inlet will affect what instruments? ASI and altimeter, ASI only, altimeter only. So now they are talking about a pitot tube getting blocked by ice. Now we have three pressure instruments. We have three pressure instruments: airspeed indicator, altimeter, and vertical speed indicator, right? So ASI, PSI, and altimeter. All these three instruments depend on static pressure for it or for their operations. So let's draw a static pressure line. So let's say this is the static pressure line. Okay. All these three instruments depend on static pressure for their operations. Now there is only one pressure instrument, which is your ASI instrument or airspeed indicator, which depends on pitot pressure originating from a pitot tube. Okay, so only the ASI instrument depends on pitot pressure. The other two pressure instruments, namely the VSI and altimeter, do not require pitot pressure for their operation. So now if the pitot tube gets blocked, let's say if the pitot tube gets blocked because of ice, dirt, or whatever, okay, so what instrument will it directly affect? It will affect airspeed indicator only. Altimeter and vertical speed indicator won't be affected because they do not use pitot pressure. They do not depend on pitot pressure for their operation. So the correct answer here is airspeed indicator only. A pitot tube covered by ice which blocks the air inlet will affect what instruments? Airspeed indicator instrument only. 72. Maximum allowable takeoff mass 64,400, landing mass 56,200, zero fuel mass 53,000, dry mass 35,500, estimated load 14,500, trip fuel, minimum takeoff fuel is given. What to find? Additional load. Okay, so step 1, draw three columns, one for takeoff mass, landing, and the zero fuel mass. In the takeoff mass column, you are going to write the value which is any value which is less of maximum structural takeoff mass and performance limited takeoff mass. So here we have only been given one takeoff value, which is maximum structural takeoff mass value 64,400. We do not have performance limited takeoff mass. So write 64,400. Next, in the landing mass column, you are going to write a value which is the less of structural landing mass and performance limited landing mass. And to that one value, you are going to add trip fuel. You are going to add trip fuel. So we only have maximum landing mass given to us. We do not have performance limited landing mass value. So write this 56,200, 56.2 plus trip fuel. What is trip fuel? 4,900. So 4.9. The 56.2 plus 4.9 is 61.1. Next, in the zero fuel mass column, you are going to write the zero fuel mass value, and to that you are going to add fuel on board, also known as takeoff fuel, the fuel in your fuel tanks when you are ready for takeoff. Okay, so what is the zero fuel mass? 53,000. Fuel on board. Uh, Fuel on board minimum takeoff fuel is 7,400. So add 7.4. 53 plus 7.4. So 60.4. So now out of these three takeoff values, your regulated takeoff mass will be equal to the lowest takeoff value. Now the lowest value here is 60 decimal 4. So 60,400 kg becomes your regulated takeoff mass value. Step number 2. Regulated takeoff mass equals to your dry operating mass plus fuel on board plus payload. So 60.4 equals to dry operating mass is 35.5, fuel on board is 7.4, payload x, so x will be 60.4 minus 35.5 plus 7.4, 42.9. So 60.4 minus 42.9 is 17.5. So payload equals to 17,500 kg. Now what is the estimated load you are currently carrying? Current load is 14,500. And what is the payload that we have calculated? The maximum capacity 17,500. So additional load will be equal to 17,500 minus 14,500, which is equal to 3,000 kg. So you can carry extra 3,000 kg with you. Okay. So 17.5 minus 14.5. Next. ATC transponder system excluding mode Sierra, mode S or mode selective contains how many modes? So there are two modes. Except mode Sierra, we have mode Alpha and mode Charlie. So we have two modes, and each of these modes has 4096 transponder codes. Okay, so option Bravo. Two modes, each 4096 codes. With mode S, you have more than 1 crore modes available. With mode Alpha and Charlie, you have only approximately 4100. With mode Sierra or mode Selective, you have more than 1 crore codes available. Question number 74. The transponder code set in an SSR system consists of what? Now this transponder code. So this transponder code is a 4-digit code, okay, forming any of 4096 different codes, 4 digits forming any of 777 different codes, 2 digits, 2 letters forming any of 4096. So the correct answer is alpha. In your transponder, your ATC controller, if you're flying an IFR flight plan or a controlled flight, your ATC controller will give you a 4-digit code that you will have to insert in this transponder. This 4-digit code called transponder code will be unique to you. Okay, every aircraft will have its own code, and this transponder code will be reflected on ATC radar screen. Okay, and this will be valid from the point of your departure to the point of your landing. Once you land, this transponder code will lapse or will get invalid. Okay, so this is the transponder code. There are 4096 possible codes, and you will be given a 4-digit code. Okay, so that code you must select. If the SSR transponder ident button is pressed, an identification pulse is automatically transmitted and continuously transmitted for 20 seconds, 4.35 microseconds before the last trailing pulse, 20 seconds, 4.35 microseconds after the last pulse, 10 seconds, 4.35 microseconds after the last pulse. Now, identification. Now, whenever you're flying in an airspace and you want to receive or you want to make use of ATC radar services, so you must first contact with that ATC controller. That ATC controller must be able to spot you, to locate you on his ATC radar control screen successfully, right? So when this contact happens successfully, ATC controller will establish or will give that notice to you, and he will give you a unique transponder code, and from there on you will be under his supervision. Okay, he will give you radar services, weather information, any other service that is possible to be given depending on traffic load, correction traffic, aircraft traffic in the airspace, etc. Now there are different ways to identify an aircraft. Okay, there are different ways to identify aircraft. Now, the first way is the ATC controller can ask you to make some turns, to make a left turn, to make a right turn. Okay, so when you make this left turn or right turn, let's say ATC controller tells you to make a left turn, 30-degree left turn. So whatever radar blip corresponding to your aircraft in the atmosphere on the ATC radar screen, that radar blip or radar representation of your aircraft on ATC controller screen will also start moving to the left hand side. Okay, there will be many radar representations, many aircraft representations on the ATC radar controller screen. Now, it's the job of ATC controller to identify one radar blip or representation and to relate that particular representation with your aircraft. Okay, so where ATC tells you to make a left turn and you start making a left turn, this radar representation will also start moving to the left hand side. That is how ATC can relate that this particular representation belongs to your aircraft. Okay, so this is one way, make left turn, right turn. Second way is to get VOR DME information. Okay, ATC can ask you to give your position with respect to a VOR and DME station. So a VOR station will enable you to find your position with respect to a radial. Let's say this is a VOR station and you are on radial 090 from that VOR station. Now, if you are on radial 090 from that VOR, you can be anywhere on that radial. You can be here, you can be here, you can be here. Okay, so you need a particular pinpoint position. So that's where DME comes in the picture. Now, along with this VOR information of radial, when you add DME information to it, you will be able to find an accurate position from that VOR station. So let's say you are at a radial of VOR radial 090, distance 10 nautical miles. That means radial 090 at a distance of 10 nautical mile from that VOR. So your exact position is somewhere here. Your exact position is somewhere here. 10 nautical miles from the VOR on radial 090. So that is another way to identify an aircraft. So if you tell ATC that I am on radial 090, 10 nautical miles from the VOR station, so ATC controller will plot that position on his radar screen and he will identify your aircraft. Now the third way is pressing the ident button. Pressing the ident button on your transponder. Now your transponder has button called, okay, there will be an ident button like this. This is just for representation purpose. So when ATC tells you to press this ident button, you press this ident button. Now when the moment you press this ident button, the representation of your aircraft on ATC controller screen will start flashing. Will start flashing. Okay. So when that happens, ATC controller comes to know that this particular radar blip or radar representation belongs to your aircraft, right? So this is the function of the ident button, and when you do that, it happens for 20 seconds. And technically what happens behind the scenes, when you press that ident button, there will be an extra pulse that will be sent to the ATC controller. Now, normally, your transponder will send these two framing pulses, frame 1 and framing pulse number 2. And between these two framing pulses, there will be other pulses that will also be sent. And okay, but when you press this ident button, there will be an additional pulse sent along with these two framing pulses to the ATC controller. This additional pulse is called special position indicator, and it is transmitted 4.35 microseconds after the last framing pulse, after the last framing pulse for 20 seconds. Okay. So remember this fact, 20 seconds after the last framing pulse. Next. Distance from Papa to Quebec is 400 nautical miles. Wind component plus 30 knots and wind component from Quebec to Papa coming back it's minus 40 knots. All engines operative speed is 160. Fuel is 2050 kg. Endurance is 4 hours. Calculate point of no return for return to Papa. What is the distance from point of no return to Q? So there are two things you have to find out. You have to find out point of no return distance and then the remaining distance between point of no return and the destination. So this is your departure. This is your destination. Let's say PNR is somewhere here. Now going outbound, you have a TAS 160 knots. TAS 160 knots and a wind component of plus 30. You have a wind component of plus 30. So ground speed will be equal to 160 plus 30, that is 190. True airspeed plus tailwind. Okay. Now coming back from point of no return to your departure, again your true airspeed is going to remain the same 160, but your ground speed will be different. What will be your ground speed? Now coming back Quebec to Papa, you are getting a headwind of 40 knots. You are getting a headwind of 40 knots. So your ground speed will be TAS minus headwind 160 minus 160 minus 40, which is 120. Now let's use the formula. Distance to point of no return equals to endurance into outbound into homebound divided by outbound plus homebound. Endurance is 4 hours, so 4 multiplied by outbound speed multiplied by homebound speed divided by outbound plus homebound. So 4 into 190 into 120 is 91,200 divided by 310, that is equal to 294 nautical miles. So distance from Papa to point of no return is 294 nautical miles. Total distance is 400. Starting to end distance is 400. So what is the remaining distance between PNR and destination? It will be 400 minus 294, that is 400 minus 294, that is 106 nautical miles. So distance from point of no return to Quebec is 106 nautical miles. Correct? Next question. The principal propagation path employed in NDB ADF system is skywave propagation, surface wave, direct wave. So the correct answer is surface wave propagation. So when you are talking about NDB system, now NDB works in the frequency band of low frequency, medium frequency, and all radio propagation happening in this frequency band is surface wave propagation. Skywave propagation happens in high frequency band. Next. Aircraft is flying straight and level over a warm air mass. The altimeter reading will be what? So, I have covered this in detail in my altimeter errors video lecture. You can find that in the playlist. I have also solved all altimetry questions from Oxford, RK Bali. So, do watch those video lectures. Your concept will be revised, and if you are not familiar with the concept, you will get uh, introduced to it, and your concept will be much very good and very strong. So do watch that video lecture. Now in just, I will tell this in short. Wherever you're flying from, let's say this is your cold air mass and this is your warm air mass. Now let's draw the pressure levels. So in a cold air mass, pressure levels descend, come down. In a warm air mass, the pressure levels start rising. In a warm air mass, the pressure levels start rising. Now let's say your aircraft, just I'm taking random numbers, 500. Okay. Now your aircraft is at 700 millibar pressure level. Your aircraft is at 700 millibar pressure level. Now altitude corresponding to 700 millibar is, let's say, 5000 feet. Okay, approximately 5000 feet. It's not accurate, but still. Now where you continue flying straight and level, okay, you will enter this warm air mass. When you enter this warm air mass, what will happen? If you fly straight and level, when you enter this warm air mass, what will happen? You will be flying along a complete different pressure level, because 700 millibar pressure level here is equal to 700 millibar pressure level somewhere little bit higher. So at this level in the warm air mass, there will be a completely different pressure level. Let's say a pressure level of 800, a pressure level of 800 millibars. Okay, a pressure level of 800 millibar. So what will happen when you are flying 700 millibar here? Your altimeter was indicating 5000 feet. Now you are flying straight and level. You are not climbing. You are not descending. Nothing. But when you enter warm air mass, now suddenly your altimeter captures 800 millibar pressure level. So the altimeter indication will be proportional to that 800 millibar. Now 800 millibar translates into some 4000 feet, let's say. So over here, your altimeter was indicating 5000 feet. Over here, it indicates 4000 feet. So the pilot finds this wrong. Okay, the pilot finds this confusing. He is instructed to maintain 5000 feet, not 4000 feet. So what will be the natural tendency? To start climbing your aircraft until the altimeter indicates 5000 feet. So your pilot will start climbing, and then once he recaptures this 7700 millibar pressure level, his altimeter will correctly indicate 5000 feet. His altimeter will correctly indicate 5000 feet. So what has happened actually? So what happens is when you fly from a cold air mass to a warm air mass, what happens? The true altitude of your aircraft increases. In cold air mass, you were here. In warm air mass, automatically you have gone to a higher altitude. You have automatically gone to a higher altitude. So, true altitude, the actual altitude between you and the ground below or the mean sea level below has increased. So, true altitude, as you can see, it was here this much. In the warm air mass, it is much bigger. So true altitude will be more than, it will be more than altitude indicated by a altimeter called indicated altitude. Indicated altitude. So this is the function. This is what happens when you fly from cold air mass to warm air mass. What is the solution when you travel to different places, and you encounter different temperatures, different pressures, keep updating your altimeter pressure setting window. Keep updating your QNS. So this error will not happen. Now this error is called temperature error. Similarly, there is called barometric error or pressure error. When you fly from high pressure to low pressure, the true altitude of your aircraft is less than indicated altitude. Okay. So when you fly from warm air mass to cold air mass, the opposite will happen. True altitude will be less than indicated altitude. Okay, when you fly from cold to warm, true altitude will be more than indicated altitude. So do watch that altimetry video lecture. It will be very useful. Okay. So an aircraft flying straight and level over a warm air mass, altimeter reading will be less than the real height, correct, greater than the real height. So the altitude indication will be less less than the real height or true height. So option alpha. Okay. Next. Minimum number of global navigation satellites required to carry out independent functions mentioned below is. Now, if you want to execute 3D operations, receive autonomous integrity monitoring facility, and you want to isolate any faulty satellite, so you will require 6 satellites for this particular function. If you want operations, if you want to find out a position, your aircraft position in space, you will require 4 satellites. If you want to carry out 2D operations, you will require for 2D operations you will require 2 satellites, 3 satellites. Okay, so 3D operations 6, operations to obtain a position 4, and for 2D operations you require 3 satellites. Next, in a Doppler VOR, the reference signal is the bearing signal, and the direction rotation of the bearing signal is what? Now Doppler VOR is technologically advanced version of a conventional or a normal VOR station. Now in a normal VOR station, what happens? I will draw a normal VOR station here. This is your normal VOR station. There will be a reference signal. There will be a reference signal like this. There will be a variable signal like this, let's say. Okay, and this variable signal will rotate clockwise. It will rotate clockwise. Now the angle between reference signal and variable signal, the angle between them, in this case it is 90 degree, is equal to your radial. So if its angle between reference and variable signal is 90 degree, that means this particular direction becomes radial 090. When this variable signal will start rotating, continue rotating, and reach a point the angle between where the angle between reference signal and variable signal is 180 degree, that this particular direction will be called a radial of 180. So this is for conventional VOR. Now Doppler VOR, same concept, slight differences. In a Doppler VOR, the reference signal is this reference signal amplitude modulated is amplitude modulated. Okay, Doppler VOR. In case of conventional VOR, this reference signal is frequency modulated, variable signal is amplitude modulated. But in case of Doppler VOR, reference signal is amplitude modulated, and the variable signal is frequency modulated. So reverse happens. And in this case, this variable signal will rotate anti-clockwise. It will rotate anti-clockwise. Okay. So they have asked us about Doppler VOR. So what will be the answer? Doppler VOR. So reference signal is amplitude modulated. Variable signal or rotation signal is frequency modulated, and it rotates anti-clockwise. So option alpha is the right answer. So this concludes the lecture. I hope you have understood all the 10 questions I have answered in this video lecture, the explanations, the concepts. I expect you have learned something new today. That's the goal of my every lecture that I do. And I request you all to share this channel with your friends. They will also come to know about this work. And subscribe if you haven't yet. Hit the like button if you have liked this video lecture. In my next video lecture, I'll return with new video lectures of or new questions from this sample paper and other sample papers as well. So I hope to see you there. See you.